Hi all, today we are going to learn new topic in nuclear chemistry. So let's start. In this video we are learning about nuclear energy. The origin of the nuclear energy is the conversion of a small amount of matter into radiant energy. If the masses of the reactants and products of energy producing nuclear reactions are measured very precisely, the products are found to have less mass than the reactants. This mass defect has been converted into an equivalent amount of energy. This conversion is a consequence of Einstein's famous formula E is equal to mc square, which states the mass and energy can be transformed into one another. The two principal reactions used as source of energy are nuclear fission and nuclear fusion. Nuclear fission, discovered by German physicists Otto Hahn and Fritz Strassmann in 1938. They bombarded uranium atoms with neutrons and discovered that some of uranium atoms split into two roughly equal fragments. This reaction is known as nuclear fission. Fission reaction produces a large amount of energy and more neutrons. These three released neutrons can be used to cause other uranium-235 nuclei to fission, producing in turn 9 to 27 and more neutrons. If the fission process is allowed to continue in this manner, an uncontrolled chain reaction will occur and the resulting explosion will release a great deal of destructive energy. One example of this is fission bombs. The enormous amount of energy released is due to the fact that the combined mass of the reactants uranium-235 and neutron is significantly greater than the combined mass of products barium-141 and krypton-92 and 3 neutrons. One type of the fission reactions is following. In the 1930s, Enrico Fermi, an Italian-American scientist, suggested that neutrons can be used in bombarded reactions because they are uncharged particles and therefore won't be repelled by the target nuclei. In nuclear fusion, two light nuclei join to form a heavier and more stable nuclei. It's the process by which stars, including our sun, produce their energy. In stars, fusion consists of a series of reactions that depend on the temperature of the particular star. For a fusion reaction to occur, high temperatures are needed to give positively charged nuclei the energy to overcome their mutual repulsion, and for this reason, all fusion devices are called thermonuclear devices. We still are not able to make a successful nuclear fusion reactor because of few problems, and they are as follows: the production of high ignition temperature, the packing of nuclei into a space small enough to allow a sufficient number of collisions, the control of the fusion reaction once it has begun, the development of materials that can withstand the high operating temperature and radiation levels of the reactor. Benefits of nuclear fusion over nuclear fission. Nuclear fusion yields more energy than the nuclear fission for given mass of fuel, and there are fewer pollution problems with the products of nuclear fusion. For this reason, work is being done to develop fusion reactor as a means of producing power. Reactors. Most physicists recognize that in controlled chain reaction, the fission could provide a continuous source of energy, and this is the principle behind the fission reactor. Fission reactors are used in the production of electrical energy as research tools and producing other radioisotopes. There are 6 components of a fission reactor: the containment vessel, the fuel rods, the moderator, control rods, the coolant, and the heat exchanger. The primary system of a fission reactor has the following components. The containment vessel. It is made of concrete and steel and provides shielding for the reactor. The fuel rods. They are located in the core and they serve as source of energy. Uranium-233 and uranium-235 are used as fuels. The moderator. It is also located in the core. It slows the neutrons so that they will be absorbed by the fuel nuclei. These neutrons have kinetic energies that are close to the energies of air molecules at room temperature. For this reason, they are known as thermal neutrons. Moderator usually consists of water containing either H1 or H2, graphite or beryllium. Control rods. Control rods are made of cadmium or boron and they regulate the rate of fission by absorbing neutrons. The coolant. Water or liquid sodium is used as coolant in the the reactor. It removes thermal energy from the core. Heat exchanger. The heat exchanger receives the thermal energy and produces steam for the generation of electrical energy by the secondary turbine of the reactor. Here is the diagram of a fission reactor. Drawbacks of a fission reactor: less availability of U-235 isotope, thermal pollution, radioactive waste disposal. The most common isotope of uranium is uranium-238, which makes about 99% of the naturally occurring elements but does not undergo fission. Isotope U-235 represents less than 1% of the naturally occurring elements. For this reason, it is necessary to enrich uranium in order to use as a fissionable fuel. Plutonium can be used as a fuel, but it is a health and environment hazardous element, and there is also the possibility that it might be used to produce nuclear weapons. The heat energy produced by the reactors contributes to thermal pollution. The fission reactor produces so much of radioactive waste which is harmful for health and environment. Solid and liquid waste such as cesium-237 and strontium-90 are placed in corrosion-resistant containers and stored in isolated underground areas. Wastes with low level of radioactivity may be diluted until they are considered harmless and then they are released in environment. Gaseous waste such as krypton-85m, nitrogen-16 and radon-222 are stored and allowed to decay until it is considered safe to release them into the atmosphere. Accelerators. A particle accelerator is a device that uses electric and magnetic fields to provide a charge bombarding nuclear particles with sufficient energy to induce a nuclear reaction. Example: Van de Graaff accelerator, the linear accelerator, the cyclotron, and the Large Hadron Collider.